form of the introduction, so yes, I'll be doing the investigating the fracture mechanisms of basic powder fusion 564 over from Stellenbosch, South Africa. This was part of my PhD research a few years back, which was supervised by Professor Thorsten Becker from Stellenbosch University at the time. He has moved to a different university now, and Professor Kim van Meensel from KU in Belgium. So that's actually in my fatigue work itself, but some of the other analysis was elsewhere. So to give you an overview, I'll give some background to what I'm doing, the motivation essentially, before some of the methodology, some of the results, what some of those results mean, and we'll finally conclude. Right, so I want to go through the whole process of additive manufacturing. It's been done, and there'll be a few more presentations on that. But simply put, 3D printing with lasers and metal powder. What typically occurs is we end up getting some type of porosity in it. We have certain types of microstructure, in this case with titanium 6Al4B. We get the smart and city microstructure. You can see the alpha prime or the Martin size, these black cylinder-like structures, where we have it in a cryo-integrated columnar structure. So the ball direction was up, and you can see this columnar-like structure going upwards. Then the other things which also tends to occur with 3D printing is the surface finish, which is typically a bit on the rough side, and large residual stress, which was mentioned previously as well. And here you can actually see some warping or delamination, that you can see the warping of the material. Now, from a fatigue perspective, often we talk about the SN approach or the self-life approach. We know when it comes to rough surfaces or porosity, particularly at the surface of the specimen, we tend to get lower fatigue life. And so this is just what's showing that the lower the density or the higher the porosity, the lower the fatigue life of the material. However, I'm more interested in the crack growth approach, or the damage tolerant approach, where we look at crack growth rate. My specific interest is the threshold region, so region 1, this region 2 being the Paris regime and fast fracture related to your K1C or fracture toughness. And when it comes to this damage tolerant approach, because there's already a crack in the system, your porosity and surface roughness doesn't influence your fatigue behavior as much as it does in your SN approach or the life approach, where there is no crack in the system in the first place. Now you already have a crack, there's already that stress intensity in the system. So it's going forward without me, okay? So what I found within literature was there's various behavior. Majority of the fatigue behavior is that it's inferior to conventionally manufactured Type form. However, there are certain studies which show that they're the same as conventionally manufactured. There are others which shows that they are better. However, whatever the behavior is, the reasons are always residual stress, microstructure, and porosity. But it's never specifically saying what is porosity improving or residual stress doing or microstructure doing. That's the reason. And what I found further as well is that different investigations will also say that primary effect on the fatigue behavior is residual stress. A different investigator will say microstructure is the primary influence. And so you get this whole diversity of reasons within literature. And so I proposed for this research that, okay, why not do threshold testing, because in this region we are more reliant on your microstructure in comparison to region 2, which is more plastically driven, or there's larger plasticity effects occurring over there. And so we get into lower crack growth rates, maybe a bit more indicative of crack initiation rates as well, but again, we already have a crack in the system. And so when looking at those research in literature,
the picture is too big. It takes some time to load.
So when looking at the threshold, region 1, or in the picture of what I explored as a part of a fusion, there's just not that many that exists at the time of doing the investigation. And then of those that do exist, they're only considering the R ratio of 0.1. So we still have that project that we was brought up on Tuesday. And so typically I just showed this one in lectures is not the best of images, but the idea is to show a crack opening and it closes. I was supposed to do some DIC work as well, but it didn't work within this specific work, but I'm continuing with that. So just to show that the crack closes before the minimum load is actually reached, and so you end up with crack closure effects, and so we need to consider that as well if you want to know the intrinsic behavior of the material. What I did was 3D printed some compact tension specimens in 3 different build orientations. So the coordinates of ZX is just perpendicular to the Z the crack plane. So Z is just perpendicular to the plane, and X is the direction of the crack itself. Other literature, they refer to this as vertical and flat. I'll just keep these pictures up as I go through. However, these two actually have the same crack plane. It's just that the crack direction is different between these two. And the specimens were built on a M2 ELC-M280 machine. Just standard parameters. I wanted the printed part. I wasn't concerned with the process parameters myself. It was just a standardized printing. Then 3 conditions. So we left one as applicated, or as built in some cases. Applied a stress relief. So this is a very different stress relief, or lower than the standardized stress relief for Type 6.4. Typically, 650 degrees Celsius is considered stress relief for Type 6.4. We did a low one for similar reason of not wanting to grow any grains. I wanted to specifically keep the microstructure the same as the fabricated one, but just reduce residual stress, and then apply a completely different one where now we do have grain growth that isn't so beta. So we do the duplex anneal, which is a 3 process, defect process print. So we just did it in the higher solid solution temperature range. The water quenching part actually brings about more insight, and so therefore we apply the second anneal just to get rid of the unwanted martensite from the water quench. Then this gives us a bimodal microstructure. So just to show that as both as well as the stress relief microstructure kind of at the same thing, never really had grain growth that we picked up. So depending on which direction you're looking at, you get columnar structure. If you're looking all direction upwards, or you're looking to the base of all direction, you get this the seed that reacts by vibrating structure. And then the bimodal microstructure, so we end up with larger alpha grains, along with secondary alpha in the matrix of beta phase as well, the white in this graph. And so then, so this is going on again without me. So just the results in the DADN format for as fabricated conditions. I won't show DADN again. I will show other forms of this. But this is just to show you. So we have, at least in the first one, which is the flat orientation, you can see with increasing R ratio, you do see a decrease in the pressure. You get that expected behavior for crack closure effects being reduced. However, in the other two, the vertical on the edge, while you do see some reduction, it's not as clear or evident as these were in this flat orientation. So a few things. But so before I get to the specifics as to why, this is just another way of representing that data. So this is for all conditions, as well as all 3 orientations. So we're just plotting the threshold versus the R ratio that was tested at. And so what I was showing over here, that we have quite a large decrease over here, but not much on these ones. You can see that this flattens out much earlier, the black one and the red one, in comparison to the blue curve, which is the flat orientation. Stress relief, we see throughout all R ratios, which get a decrease. So the idea here is that there's less residual stress, and we're seeing expected behavior. Although on different scales, these values were actually the same for all 3 orientations, but the behavior to get there was different. And then for the bimodal microstructure, the duplex anneal heat treatment, we end up getting a lot more evidence of closure behavior, crack closure behavior. Then another way to perform this, or to alter the results itself, is to look at it from a threshold versus maximum stress intensity. So I think it's worked by Suvidin, I forget the name correctly, but they proposed a two-parameter approach, which I know Rafici and associates also sometimes use this approach, a two-parameter approach, where they look at, it's not just about the delta threshold, but also about the K max value, critical K max value. And when you plot it on this type of graph, you see that there is this difference behavior. You have a somewhat vertical behavior first, and then a somewhat horizontal behavior in your threshold as you increase your, in this case, K max or your R ratio. And the idea is that this somewhat vertical portion is more affected by this crack closure effect, so roughness, use of plasticity, maybe, where once you get rid of that and you have higher R ratios, then you don't have closure effects anymore behind the crack tip, and so it becomes what's more intrinsic to the material. And so yeah, it's what they call closure affected and closure free regions. So the mechanisms change accordingly. Again, what was interesting is when looking at the micrographs and the fracture surface, so when looking at, this columnar grains, when you look at the fracture surface, you actually end up getting fracture features which are quite similar to the microstructures, columnar structure. And I just highlighted one of them over here. Of course, within the same, depending on how you tilt your thing, you get the better contrast and lighting. So not necessarily the best over here, but what Alch was showing was that you have these private grains with different amounts of roughness within each of them. They all have slightly different amounts of features. When you look at the other orientation, so the edge orientation, again, a more perceived equiax private grain, same thing happens on your fracture surface. And this is for your stress relief as well as asphalt microstructures. And again, different amounts of roughness is in it. So just to show all three. And so this can relate to, so just one more step is that what we can do with these different roughness is that when you look at the crack path, then what we actually find within certain ones of them, particularly the ones which show the roughness, we actually see that the crack path is deflected by these off-prime lacks. And then we can associate that as well with these facets that we start finding, which then from a pri-beta grain perspective, there is a relationship between your pri-beta grains and your alpha-prime lats, known as the Burgers orientation relationship, which gives about 12 variations as to what angle that the alpha lats can take, with approximately 45 degrees being one of those ones which are more dominant, and we actually see that the crack path is affected, at least in this case, by those ones which are more aligned with 45 degrees. Right, so just from a schematic perspective, if you were to think of the crack front meeting those beta grains, then you can see that for this orientation, the flat orientation, it should receive a larger amount of crack closure per unit area or per unit length of crack front, because that's the way the beta grains are aligned with the crack front based on the orientations. And so when looking at the results, that is what we observe, is that the flat orientation is the one that shows larger reductions in your fatigue behavior. So we associate that fracture with it, so that the roughness-induced crack closure. And in terms of why these two are a bit more flat earlier on, is if we consider the residual stress, and so we measured the residual stresses in the crack planes. We used the the crack plane, and used the CMM machine, a coordinate measuring machine, which just measures the height of that surface of this deform, and we can then translate that into residual stress. And what we see is then the edge orientation as well as the vertical orientation are the ones with the highest stresses in them, particularly stresses as tensile, with some compression in the center. After the stress is applied, then we end up with less. What we also found was that we measured the crack opening displacement of those specific specimens. The ones which were as fabricated, so has residual stress in it, and the ones which have stress relief, we do find a difference in the apparent stress intensity or opening stress intensity. And so we can then associate these two, which has the highest stress intensities, with this behavior, which shows less crack opening in comparison, less crack closure in comparison to your flat orientation. I don't need to wrap up, so I did some DIs on the bimodal microstructure. So in this case, we actually end up with larger grains, a beta phase. So in both cases, the larger grain is more ductile, the beta phase is more ductile than alpha phase. And then there's also now an alpha beta interface, which allows for more crack tortuosity and branching and bifurcation, which occurs in different orientations, which ends up resulting in higher amounts. We didn't really see much. Well, while I am pointing out prior beta grains in here, it came across more rough and specifically within a structure. We had more faceted fracture that we could observe, in particular on the head orientation. So now you need to consider your Schwind factors and which prism, which slip plane is activated between your basal, your prismatic and your pyramidal slip planes. So yes, okay, I just need to back it up on there. And so we ended up with a higher threshold with our bimodal in comparison to these fabricated essentially. And then to conclude, so we associated crack closure with the prior beta grains, the relationship between the alpha and the prior beta grain. The duplex and neo bimodal ended up with a higher threshold due to its alpha grain size and the phases of the beta, as well as our residual stress showing some anisotropic effect. Thank you. That's it from my side.